It's my great pleasure to welcome you to this conference to honor Sergiu Klainerman. We are met to celebrate the achievements of a wonderful mathematician, Sergiu, whose vision dominates the field of geometric nonlinear partial differential equations, in particular equations of hyperbolic type, and the mathematics of general relativity. His ideas, his work, and his influence have transformed these vast subjects. So, to celebrate Sergiu and his mathematics, the organizing committee has prepared for us a great program of speakers that we are all now eager to hear. So without further ado, let me just finish by expressing our thanks to those who have done the hard work to make the conference possible, the staff of the math department, and in particular Scott Kenny and Will Crow. Before we start, I've been told that Scott has a few words of importance for the conference. Scott.
This is a first for me. Welcome to the math department. It's nice to see so many familiar faces. Some of you are almost as gray as I am. I just wanted to go over a few of the practical details connected with the conference. Out front, you'll see there are campus maps, and I've tried to indicate where lunch places will be for you. I suggest you go close. I drove through Nassau Street twice. They did a terrible job shoveling. Some of you have already registered for the banquet. There is limited seating available. Those of you who have registered will pick up confirmations from me outside at tea time today. I believe, and I'll check when I get back to my desk, there are a handful of seats available. Those will be first come, first served, so see me at tea time. Last but not least, those who have been offered reimbursement, I've posted signs outside. You're going to need to see my colleague, Linda Brajna. She's on the 3rd floor of Fine Hall, room 306. She'll help you. The university has a wonderful reimbursement process, and you can sign your life away with her by filling out numerous forms. Somebody asked about Wi-Fi access, and my colleague, Will, who knows all about these things, says that there are 2 networks. The first is called PU Visitor and needs no password. Hopefully that means something to you because it means absolutely nothing to me. And the second one is PU Wireless. So if you have any questions, see Will, who is seated here, and he'll be able to point you in the right direction. Again, it's nice to see you all, and I hope the conference goes well.
Okay, so we are ready to begin our birthday conference. Happy birthday, Sergiu. Our first speaker is Peter Constantin of our department, and he will speak on the inviscid limit. Peter.
No, it'll turn on in a second. Just
do I put something on?
if you would click this on.
Okay. Is it on?
It's on.
Right.
Pocket.
Pocket. Okay. All right. Do people see and hear? Is it on? Yeah. Okay. Let's see. Good. So, I'm the first speaker because the organizer thought that I know Sergiu longer than his wife knows him. And that's an understatement. I was thinking this morning, do I know him for 51 years or 50 years? So we were from Bucharest. 51 years ago, I had a girlfriend on the same street as Sergiu. I remember your dog, Lucas. I don't remember if I knew, I was 14. I don't remember if I knew you when I was 14. But I think that's, by 1968, we were protesting the invasion of Czechoslovakia by the Soviet armies in front of the Soviet embassy. A handful of us. That was sorry. So I'm.
I'll just make it loud.
All right. So this, how is this now? It's good? All right. I can hear some. So yeah, that was not such an act of courage as it might sound, because at that time Romania was not mobilizing its army at the borders, afraid of the Russians invading it. So, but it was nevertheless filmed by the Soviets inside, so we had fire. So in high school we were interested in philosophy, and as you know, Sergiu is anything but a very frivolous guy. So we're reading Kant and Hegel for fun, and with a bunch of colleagues, and then went to the university and listened to lectures on history of mathematics by Imre Toth, who was a philosopher who ended up by being a Trotskyist in Germany. Another of, as you know, left-wing leanings of Sergiu originate from those times. So after that, we went actually and we took classes at university in high school, and he's a year older, but we ended up by doing lots of things together because there was not a lot of PDE, and those times we were thinking about learning PDE, and we did this kind of privately with another researcher named Otto Lies, who was older than us. And so we emigrated out of Romania within a few days of each other, ended up in different places. So our life separated for a little while, and then I visited New York. And I want to say a few things, especially for the younger people, about Sergiu as a young man when he was doing his early work after his PhD, but when he was doing already, or during his PhD, and he was doing already the method of vector fields and things like that. And what you may probably don't know very much is that Sergiu worked hard on hard problems in fluids. So I remember pages and pages of calculations on the Euler equations, second derivative of the variance, pages and pages and pages. And I didn't ever tell you this, Sergiu, but you influenced me a lot. So the influence that, first of all, this kind of relentless search for the real thing, deep and without any compromise. And this is Sergiu. So no shortcuts, no abandoning, no transforming the problem into models, of course, models as stepping stones, but no compromise. And great depth. And somehow in those early years, it's not clear it's going to pay off. It's not like you are a famous professor in Princeton. You're just a young person working on something and not giving up. So he has, of course, and you will hear from others who are actually more informed about his work in relativity. I was witness to the part in the early beginning of nonlinear wave equations, and I'm not going to get into lots of details, but again, even the method of commuting vertex fields influenced me a lot, and I thought there are a number of achievements that he had that were eye-opening. Another thing that I remember, and probably you don't remember, I was shocked when I visited Courant for the first time, and we were talking about some math problem, I don't remember what, and he asked me what's the physics, I was talking about some technical stuff. So he was asking me about the physical interpretation. This is Sergiu, and I, at that time, had no idea what he's talking about. Who cares? And so that influenced me also a lot. So I think that there are other things that maybe are better for the banquet, so I will be just saying that for the young people, the example of going for the deep, serious, uncompromising, big problems is an example that's worth following and is exemplified by Sergiu. So I'm going to talk on the inviscid limit. This is somewhat a little bit lateral from the original interests of Sergiu. As you probably know or should know, he has written with Andy Maida a very influential paper on the limits of zero Mach number, but this is a limit of zero viscosity or high Reynolds number. And there are a number of issues that I would like to talk about. So now I need a chairman. So we started when? Let's see, when should I end? Alex, I mean, the organizing committee, let's get a decision. 50 is plenty of time. So I'm aiming for 10:50. Okay? All right, I'll try to zip through this. So it's also morning, and I'm assuming this is a talk for PDE people, so I'm assuming, therefore, that we're going to talk about physics. So let's remind ourselves the notation here. Let's see if I have this faint green thing. Okay, so we're going to call U the Navier-Stokes solutions, which is the solution of the Navier-Stokes equation, and here is the equation. I'm not going to put the nu here, okay? So it's implicit in the fact that it's Navier-Stokes. And the Euler equation will have a solution called V, or U Euler, or the solution of Euler at time t, and here is the initial data, U0, okay? So that's the Euler equations. Boundary conditions are different. This is going to be about inviscid limit. So the boundary conditions, the classical no-slip boundary conditions for U is adherence to the boundary, so the particles don't move on the boundary, U is 0 on the boundary. And for the Euler equation, there is non-penetration, so there can be slip on the boundary, but the normal component of the velocity is 0 on the boundary. And there is something called the Reynolds number, invented by Mr. Reynolds experimentally, which is that you associate to a flow a non-dimensional parameter, which is called the Reynolds number, where U is a velocity, so you have a length size and time size, some units, and in those units you compute a typical velocity of the flow, length divided by time, and then the viscosity, kinematic viscosity, is a parameter that's a material parameter in some weight, in some system of units, and this is the Reynolds number, and flows with the same Reynolds number have the same behavior, and that's the observation of Reynolds, and that's why you can test an airplane in a wind tunnel by scaling everything down. And in mathematical terms, if you want nu to be 1, then you have the parabolic scaling L squared over t equals 1. So t is L squared, and then you can have this one parameter family of solutions of the same equation with nu equals 1. These are the same thing. So in the few, so I'll tell you a little bit about the organizations over the talk. I'm going to give you, first of all, a couple of background statements about the physics, where the problems come from, and then I'll recall some of the results, and only at the end I'll mention some very modest new results. So for the viscous flows, in general, for turbulence, u is not just the velocity, but it's the departure of the velocity with respect to a mean. So it's a turbulent fluctuations. You can think of it as the mean being zero. The zero is transported by the flow. So you can think of the Navier-Stokes equation itself as an equation for the fluctuations. There is an observation of the constancy of energy dissipation per unit volume. So here I wrote it in this fashion, in the fashion in which it is measured in labs. You have references, you have high Reynolds numbers of the order of 10 to the 6 or 10 to the 9. These are because we do numerics and some controlled experiments. And u is the mean square average of the velocity, space-time average of the square. L is an integral scale, which can be a size of apparatus or is defined in terms of the spectrum that you observe. So these things are measured, and then the statement is that there is a constancy of, so large number of physical experiments, different situations, large number of numerical experiments, and C is observed, computed, and plotted by Srinivasan, for instance, against many, many, many different situations. And this is a very generous range. Actually, people are trying to say that C is a universal constant depending on the boundaries or the forcing. So that means, let me quote from Uriel Frisch's book, if in an experiment on turbulent flow, all the control parameters are kept the same except for the viscosity, which is lowered as much as possible, the energy dissipation per unit mass, this is rate of change in time of the energy, kinetic energy of the fluid, behaves in a way consistent with a finite positive limit. So the EDT is average energy dissipation, and if you're believing in the Navier-Stokes equations, that's the average of viscosity times gradients of u squared. And that being constant in the limit of zero viscosity says that the gradients have to be large in the limit of zero viscosity. So that's let's say, fact, because it is a physically observed fact. Uriel Frisch states it in a very cautious way, but mathematically you ask yourself if this is really true. Another important law is the 2/3 law, which we're going to mention. So let's quote from Frisch. In a turbulent flow at very high Reynolds number, the mean square velocity increment between 2 points separated by a distance L behaves approximately as the 2/3 power of the distance L in the inertial range. So that means I take velocity here plus L minus velocity there, square, or do the correlation. And this is of the order dimensionally epsilon times L to 2/3. 2/3 means that it's kind of like Hölder of order 1/3, and the coefficient is the same epsilon that we discussed in the previous slide. Length has to be larger than a cutoff, and this cutoff is a dissipative cutoff, and an associated concept, which is rigorously related by Fourier transform of the correlations, is that the energy spectrum, so the density of Fourier transform at shell k, is proportional to k minus 5/3, and this was proposed by Kolmogorov in 1941, and it turns out experimentally that it's true, again, with a universal constant and the epsilon measure. Okay? K also is, these two numbers are related, so Kd is related to viscosity and epsilon. So the story here is that if you are in wave numbers bigger than Kd or lengths, smaller than Kd or lengths larger than the corresponding physical length, then you see a certain behavior, and below that you see viscosity operating and finishing off the job. So making actually this turning the minus 5/3 to an exponential decay. So the questions that are raised in this, and they are the leading questions on this problem, are, first of all, is the dissipation bounded away from zero? Is the 2/3 law true? And are there high Reynolds number universal asymptotics? And these are vague questions. I've not specified them enough. They need further sharpening, but they are thematics. So these are the themes. They form the background for studies of singularities and inviscid limits. So in the back of your mind, if you're studying singularities or inviscid limits, you should kind of think that you're addressing these questions and framing them a little better, maybe, and making precise statements about them. Okay? So let's talk about inviscid limit a little bit. So I want to distinguish between time and zero viscosity limits because they do not commute in a trivial manner if you have, let's say, even 2 dimensions, so we don't wonder about regularity or not. If you take time to infinity and do not force the equations, you get 0 in Navier-Stokes, whereas if you take viscosity to 0 first, you get an arbitrary solution of the Euler equations, which remembers the initial data. So it's a really very different limit. In the case of forcing, this is not a theorem, but it is in non-zero forcing, not for all of them. So there are 2 limits. If the time interval is fixed, in the absence of boundaries, so that is periodic boundary conditions or decay at infinity, then the inviscid limit for finite time leads to the initial value problem for the Euler equations. Okay, so I'll mention that in a second again. So I'm reminding everybody things they know. If you take time to infinity first and only then the Reynolds number to infinity, then you get selected stationary statistical solutions. So first let me mention that this is the turbulent regime. If you have an experiment, for instance, the experiment of a Rayleigh-Taylor, or Taylor-Quet, I meant, Taylor-Quet experiment in which you have 2 cylinders, fluid between the 2 cylinders, one of them is rotated, and then measurements are made on the correlations inside the fluid, then what is observed is a stationary state, a statistically stationary state, and not an initial value problem. Things are settling down. And in that case, what you're doing essentially a measurement of the solution for a very long time, and then consider the parameter in the Taylor-Quet case is the rotation that you're applying. In the Rayleigh-Benard question, it is the hit that you are supplying, so they're parameters. They a limit of those parameters making the Reynolds number going to infinity, and that gives you a measuring function space from each observation, and those are the objects that you're going to study. That's the inviscid limit in the long time. It's a very tall order. It has begun to study by Hopf and Onsager, and after that by Foyash and collaborators. So that it's not vacuous, but it's a very hard subject. So if there are no boundaries, it's well known that if the initial data and time are fixed but arbitrary, and if the solution of the Euler equation is smooth on a time interval, maybe long, but because somehow the Euler solution is nice, in Sobolev space of high enough order, then there exists a viscosity such that for all smaller viscosities, the same initial data, Navier-Stokes, is smooth. And the difference between the two in Sobolev spaces of lower order vanishes to the natural, like the coefficient difference between the 2 equations. And so that's a statement in arbitrary domains or in the whole space. There is a gap here that's bizarre. If nu is very large, again, things are good in Navier-Stokes, they go to 0. If this nu 0 depends on time and nu 0 in the proof, so it's an artificial gap. It would be interesting to fill it. Swan in 71 and Kato did this for short time. I did it for arbitrary long time. Masmoudi proved that the converges in HS, but for shorter time, just any shorter time than this one. For less smooth initial data, vortex patches, that means functions with gradients, curls, L infinity and L1. This is still true. The convergence to Euler still holds, but the rate deteriorates, goes to nu 3/4. This was done, the sharp one by Abidi and Danshan. We did it with Jiahong in 95 with square root, and Masmoudi in 06. And an interesting additional result is a result by Bardos and Titi, that any L2 weak limit of Navier-Stokes is a dissipative solution of Euler. So dissipative solutions are a weird concept, but if a smooth solution exists, then it's a dissipative solution. So in other words, in particular, if a smooth solution exists, then any weak limit is a solution, is that solution. Okay? So that's a strong result, actually. Okay, but because L2 weak limits of Navier-Stokes do exist. Okay? It's a very easy to prove result, too. All I'm going to talk about today will be easy to prove results. Hard to prove results are usually the realm of situations in which you know how to do the easy ones. We don't know how to do the easy ones here. Okay, the Onsager conjecture, I will mention it quickly here. So this is somewhat related to the 2/3 law, but it's finite time initial value problem for 3D Euler. So it's not a long time inviscid limit. And the conjecture by Onsager was that solutions of the Euler equation, this kind, conserve energy if they are smoother than Hölder with exponent 1/3. And for S less than 1/3, there exists a solution S or equal, I should have put it. So this is a typo. This is smoother than 1/3. This should be including 1/3. Exist CS solutions for which the energy is dissipated. And the easy part was done by a bunch of people, and this state of the art is that if U is in L3 with values to a Besov space, which is essentially a little smaller than B13 infinity, okay, so the coefficients here have to go to 0, then conservation occurs. So essentially, anything better than 1/3 and L3 in time gives conservation. And then there were examples of wild solutions, Schaeffer compactly supported in time, and Schnirelmann dissipating energy, bounded in L2. And then the famous developments by Delelis and Sekaidi, convex integration, H principle of Nash and Gromov, and use of Beltrami flows, and use of the strategy of diminishing Reynolds fluxes. For those who know, they got S less than 1/10, and then Phil, who's here, noticed and used these ideas, but used the fact that the Lagrangian derivative is better behaved than the time derivative, and used some nonlinear phases in this oscillation that you put, and got 1/5. And then everybody returned to the original the combination of these ideas, did a little better time cutoffs and such, and the current result is L1 with values in 1/3, C 1/3. So L1 in time versus L3 in time, actually versus L2 in time. It's a big gap. It looks technical, but it's actually a very big gap. Sorry?
1/3 plus. Or you think that's not true?
No, this is, okay. So this is sort of like conservation in 1/3 plus some information that's huh? Yeah, so this is 1/3 minus, but it's 1/3 minus. Okay?
The last result shouldn't include me.
What?
The last result shouldn't include ISO.
Should not include you. Are you sure? All right. For a long time and no boundaries, there are no results for 3D Navier-Stokes and Euler. So we're going to go quickly towards some scandals. Okay, the first scandal will be soon. So in 2D Navier-Stokes, so let's do things we can do. 2D Navier-Stokes where there is regularity, there cannot be anomalous dissipation of energy. There is a priori bounds for the gradient of U in L2. You remember the epsilon was nu times some average of this guy. The average of this guy is bounded. Nu goes to 0. You get 0. Okay? So let's look at the vorticity, which in 2 dimensions is the curl, the gradient perpendicular of the velocity. So it is transported in 2 dimensions and forced. And it has, therefore, a simple energy balance. You multiply by omega, integrate by parts, you get some balance. And therefore, you have now the question, what happens in the limit of 0 viscosity, long time, with this quantity? And the limit of this quantity averaged in time has a name. It's in turbulence, it's a Krachnan dissipation. And Krachnan in 68 proposed the theory of 2D turbulence based on the fact that this doesn't vanish. And in 2000, Bernard said that if you add damping to the equation, we'll see the damping in a second, then there is no dissipation, anomalous dissipation. So, yes, that's true. If you add damping, here is a schematic way of writing Navier-Stokes equation. You put here a coefficient that's positive, and then this is the Laplacian, and this is the nonlinearity, including the pressure. So you have a force Navier-Stokes, you do long time, then you take this object, which is the time average of the gradients of omega square, which are the dissipation of entropy, not energy, and take viscosity to 0, you get 0. So that's a circle of ideas where this is using it's using statistical solutions, and we did it with Andrei Zarfolia and Vlad Vikol for SQG of the same type, critical SQG. I'm not going to talk about SQG today at all, but I wanted to mention that it's a broader, let's say, class of equations for which you do this. So here comes the first scandal. There are computations of Gallet and Young and some arguments that in 2D periodic undamped, no gamma, forced by Kolmogorov forcing, in particular forcing here, there is what's called a condensate. A condensate, it's simply that there is a stationary or quasi-static solution of the equations that is bounded in the limit of 0 viscosity. So these things concentrate at the large scales, some large vortices form, they're stable for all time, okay? So there is a process in 2 dimensions in which from small scales you start with random initial data and you wait a little bit, you use Navier-Stokes, and the things are cleaned up and larger vortices emerge. The small vortices merge and create larger vortices, and in the end somebody survives as you are still stirring the fluid. And that's called an inverse cascade if it is statistically steady, but even in the case of only 2 vortices, it's a process of increase of a scale. So this is numerical, it's semi-analytical, it's analytical in somebody's sense. It's wrong for some solutions. So for some solutions, you can solve this problem, time-independent problem, by balancing the solution with the Stokes operator with the force and making the Euler part 0. And that obviously will go to hell as you divide by nu. So it's unbounded. It's not. However, the problem is to construct an F so that a stationary condensate exists. And it's a problem because numerically you see this. I mean, I don't know to what extent the numerics will live forever and all that. But important observation is that the steady Euler force is easily solvable, and you can even declare it by any kind of nice state. You take a number of modes that all live on the same shell, and you can create a nonlinearity and declare that to be the forcing. So you have lots of steady solutions. The problem is, however, can any steadily forced undamped Navier-Stokes solution remain bounded for all time as the viscosity is removed? So you take Navier-Stokes, you are free to design your forcing. You take Navier-Stokes, you take long-time behavior of these solutions. They are bounded, but bound depends on viscosity. You remove those bounds and they stay bound. Okay, so that is totally not known, and it is really something that would require the balance not of F with this, but F with Euler, and you need some sort of friction. I'll end with this kind of questions in the end. It is a real phenomenon, and we don't know how to do it. So let's go back to the problem that I'm going to talk about, really, and that is the finite time with boundaries. And let's see what are the known results here. So in the inviscid limit, we're going to consider the same initial data because it's for finite time, fixed time, smooth domain. And the question is the Navier-Stokes going to the Euler inside the domain, weakly or better? Okay? So Kato, this is the K Kato. There will be another Kato at the end, the C Kato. So remember that. It's an exercise for you. We'll find out who's that C Kato. So if the dissipation, which is nu times gradient u square in a boundary layer goes to 0, as nu goes to 0, and the boundary layer is essentially the boundary layer of order nu around the boundary, okay? Then this convergence holds. Actually, it holds in L2, okay? So there is assumed a smooth regime, by which I mean this guy, U Euler, is smooth, and a smooth boundary. And the method is a method of corrector. You'll see a corrector in a little while. So there have been improvements of this. You don't need the full gradient. You can do only the tangential gradient in slightly thicker, not O of nu, but slightly thicker boundary layer. And those were done by Temam and Wang. And Bardot and Titi result that I said before in the whole space is also, there is a variant in the boundary, and it says that if nu times the normal derivative of the tangential component of Navier-Stokes goes weakly to 0 on the boundary, then any weak L2 limit of Navier-Stokes solution, it's a dissipative solution of Euler up to the boundary. There is a modification of the notion of dissipative solution with boundary. Actually, they have a little bit of a typo on the paper, but it's correct. The inviscid limit is known unconditionally, meaning I have only conditions on the initial data and nothing else, only for a very short time, and real analytic data. Very short time means you don't let a little eddy to turn over. Or for, this is a classical result with Cafish and Sammartino, or for short time and vorticity supported away from the boundary before it has a chance to get close to the boundary. This is a recent result for Maekawa. And then there are restrictive symmetries. This is the Helena Nussenzweig-Lopez and Lopez-Filho and Anna Mazzucato, and Mazzucato and Taylor and Kelleher. So around 1904, Prandtl proposed a asymptotic development of the Navier-Stokes solution, saying it is the Euler solution away, please note here square root nu from the boundary. Then there is some corrector, which is called the Prandtl corrector, or the Prandtl equation, in a square root nu neighborhood of the boundary, and then the rest is going down to 0. So, and UP solved these Prandtl equations, and know the Kato's boundary layer is much smaller. It's order nu, and this is square root. Okay. So the Prandtl equations are ill-posed. The expression is not bad. And the equations blow up. Okay? So, but we don't give up. All right? They are well posed if there is no turning point of the Euler flow on the boundary and the initial vorticity is bounded below by a positive constant. So this was done by Oleinik in 66 in using some nonlinear change of variables, and by Mahmoudi and Danny Wong in Sobolev spaces in 12. So you will see the condition again, but essentially the velocity points one in one way, so there is no turning of the point, and it's also it has some monotonicity property, which is this vorticity being bounded below by a positive constant. If the initial velocity is real analytic in all variables, this is again in the same like the inviscid limit, or if the initial velocity is real analytic with respect to tangential variables and smooth transversally. And these are more recent results of Igor and Vlad Vikol and Canone, Lombardo, and Sammartino 01. And also, I think this is the world record. I'm not so sure, I'm not an expert, but I think so. The initial vortice has a single curve on non-degenerate critical points. Remember that the and it is Chevreul 7 quarters in the tangential direction and smooth transversally, and this is Gervais and Mahmoudi 13. Okay. So let's talk about the problem a little more in detail. So let's consider only the upper half plane, which we call omega now. The velocity, the Euler velocity is assumed to be super nice. Let's say that on the boundary, the horizontal component, so the drift part of the Euler solution is called capital U. It's a smooth, beautiful function. And we assume also the Navier-Stokes solution is smooth all the way to the boundary. And remember the vorticity, it's the curl of the velocity. And we assume that the initial data are totally the same. So we're putting ourselves in the simplest possible situation. And the boundary conditions are thus u is 0, the Navier-Stokes guy is 0, v2, the vertical component of the Euler guy is 0, and v1 is capital U. Okay, so these are notations. So I have two results that I want to mention and a little bit about their proof, and that's it. So here is the first assumption. The first result is with Igor Kukavica and Vlad Vikol, and it's complicated to state. So the first assumption is that the velocity is pointing in only one direction. The horizontal drift doesn't turn. The second is a condition on the vanishing of the average dissipation, or this is the vorticity, but it is in a Kato layer, and the object that you are computing here is not a vorticity. It is nothing unless the vorticity is very negative. And how negative? It is essentially like -1/nu. So if you are not more negative than -1/nu, and if you are in a boundary layer that's a little thicker than Kato, then you have the L2 you convert strongly in L2 to the Euler solution. So the conditions are the Oleinic sign condition, but it's a one-sided Kato condition for the inviscid limit. So it's a combination of Oleinic and Kato, essentially. The result works in bounded domains with certain boundaries. It uses a better corrector. You're not going to see the idea of the proof of this because I have another one that I want to show you. And the better corrector has sign condition. And it's non-vacuous. There are, if you take viscous shear flows, then which are solutions of Navier-Stokes, then they'll satisfy this. The condition of non-turning can be removed in some cells, can be put only on the initial data, and you have nice solution of Euler, so that is okay. But there is a condition of vanishing. As I said, the condition in particular, it says that if the vorticity doesn't turn very negative in that Kato layer, a little thicker than Kato, then we have. So what happens here is that Oleinic condition was that this is bounded by 0, a little strictly above 0. And you actually can go much, much lower negative. And I'm recalling the Bardos entity, and actually Tariq Elgindi and Gautam Iyer had also discovered this by themselves, that if you have weak convergence on the boundary, you do get, and if you have the weak solutions are dissipative solutions. All right, if there was a turbulence context, there isn't, because turbulence is about statistical behavior of fluctuations, but there is something called the friction velocity at constant density, which is the square root of the wall friction shear stress. The wall shear stress is nu times the vertical derivative of the horizontal velocity, but on the boundary of Navier-Stokes, this is the same as the vorticity on the boundary for flat boundaries. And there are wall units that gives you a length scale that is just simply viscosity divided by this u tau. And the statements that we have suggest that if the wall shear stress, and hence the u tau, vanishes in the limit of infinite Reynolds number, then there is no backflow, there is no turbulence. Okay? So turbulence is generated by the absence of this condition. And the absence of these conditions is generic, actually. All right, the result number 2 is with Tarek and Mihaela Ignatova and Vlad Vikol, and it's a simpler and in some senses, I like it, but I'll explain a little bit why. It's because of this condition. So assume that the time average of the maximum square velocity is bounded independent of viscosity. That's the assumption. We need an additional assumption, and that is that the product U1, U2 is equicontinuous at x2 equals 0 on the boundary. Remember that this is 0 on the boundary. So what we need precisely is essentially a very weak bound, so there is an integrable function such that for every epsilon there is a height rho epsilon, so that if you are below that height, the vertical direction is less than below that height, you're less than epsilon multiplied by this integrable function. Okay, so if gamma would have been a constant, this is really equicontinuity. It's a little broader than equicontinuity, but we don't really need it. Okay, so then of course the statement is that if this condition and this condition are satisfied, then you have inviscid limit. So what does this actually mean? It means that the Lagrangian image of the Prandtl boundary layer stays a boundary layer. So because you're not shooting, you're shooting at, in time t, you're shooting at distance integral in time of UL infinity, and not farther. So this is dominated very easily by the square, which is an actual natural condition in Navier-Stokes. For people who know regularity, this is one of the so it's a very natural non-dimensional condition. And it says that inside the boundary layer, if you start inside the boundary layer and that units of time and that length of time, you don't go maybe twice as much, but not, don't change order. So that's the assumption. A corollary is, actually it's a corollary of the proof, if you assume that the horizontal derivative of the horizontal velocity is uniformly integrable near x2, which means simply that locally, if you integrate it, you get something small, provided the rho is, the height is small enough. Then again, you have the convergence. So let me show you a little bit about the corrector for this one. So what is a corrector? A corrector will be a function that you invent that takes care of the boundary conditions. The two boundary conditions are different for the Euler and the Navier-Stokes. The Euler is slipping on the boundary, Navier-Stokes doesn't. So you want to correct, you produce a function that slips the other way, minus u, on the boundary, and that function should be inserted in the calculations and do the job of helping you go to the limit. So in this particular case, a very simple one. No, no. You'll see what it does. You'll see nothing does. It's not a solution of Prandtl. So you don't have enough control to actually do the Prandtl, and actually sometimes the Prandtl is wrong. So this is, but at the end, this doesn't do totally the job because we have assumptions. So this is a Gaussian, so it's a solution of the heat equation. If you think of what I'm doing here, I'm changing the variance so that it's the heat equation. And you compensate for the mean of this away from the boundary. So this is supported away from the boundary, okay? And delta of t is not the delta function, it's simply 2 times, square root of 2 times nu t, okay? And it has the correct average, so that this will have average 0. And phi 2, this is the horizontal component of the corrector. The vertical component is just simply so that it's divergence free. So you just integrate the derivative. And then this has the following properties: divergence free. It cancels the contribution on the boundary of the, so now it makes this object have full zero boundary conditions. It is caloric. It's heat, it's actually, instead of being Prandtl, it's caloric. It simply solves a small heat equation. And then the horizontal components are small in LELP. Of course, other than infinity. And they're, phi 2 and its horizontal derivative are also small, actually delta in all LPs, and the vertical costs you 1 over delta, as it should. So the idea of the proof, you take the difference between u and the corrected Euler. Now W is 0 on the boundary, so you can do L2 bounds. You get a bunch of terms. They look like so. And for instance, this guy is Navier-Stokes, Euler, corrector, Euler, W, this W that we're doing. And remember that V is smooth, gradient V is bounded, all that. Phi is small, and I'm not differentiating phi, and U is bounded in L2. So for instance, this is good, very easily good. And then the interesting term, the corrector was designed so that the heat guy is small, but time derivative, but we're going to do time averages. And that's because I solved the heat equation in G sigma, and U and U tau is good. And then the average of the first term, which had this guy, is vanishing. And the bad guy is the nonlinear term, where there are derivatives of the correction, and if the derivatives are not in the vertical direction, that guy is okay. And the main contribution is from the vertical derivative of the correctors, and now you can see U2 times U1. So this essentially looks like a Gaussian and a nice function, and U1 and U2, the product, evaluated at delta times x2, and that is going to be small if I assume it is small. So it's 0 at delta equals 0, but I need uniform bounds. So then you do the bounds, but you use the assumption on this assumption for near the boundary layer, and then outside the boundary layer is trivial. Okay? So that's the basic idea. And for the corollary, there is a similar bad term. So in the corollary, we have assumptions on the derivative, horizontal derivative of this guy. There is a similar bad term. And then if you are far away, you just simply use the fact that these guys are very good functions. So the integral far away is small. And then inside, you use the fact that U2 is the vertical derivative of U2 minus 0. But the vertical derivative of U2, the 2U2, is minus d1 U1 because of divergence free. And that's a derivative with respect to the horizontal variable of the horizontal guy. And this we assume that is good. So that's all. Okay? So then you have, in the end, you put together these two bounds and you get order epsilon modulo objects that you assume they're finite. Essentially this thing. So, in conclusion, now I remember that we talked about Kato with K. Now I'm going to talk about Kato with C. Kato with C is reported in Pliny. It's Cato the Elder. Cato the Elder finished all his speeches with Delenda est Carthago. Carthage needs to be destroyed. And Carthage needs to be destroyed, and it was destroyed in the end. It took some 50 years after he was talking. But they destroyed it because they didn't like it. And that is used in oratorical situations in which some speaker talks about some subject, and unrelated to the subject, he always ends up with the same subject. And in my case is Navier-Stokes regularity. So remember the Burger's equations in 3D? This guy does not blow up because it has a maximum principle. And because it has a maximum principle, it's bounded in L infinity, and in particular that integral from 0 to t of UL infinity squared is finite, and then you just apply a crank. So the pressure for Navier-Stokes regularity question is everything. And if you remember, and you probably do, there is a theorem by Charlie Pfefferman and I that if the gradients of the direction vector field of the vorticity are well behaved, then there is no singularity in Navier-Stokes. In other words, if the situation in 2D is that all the vorticity points in one singular direction, the gradient of that is 0. If the situation is somehow coherent, then there is no blow up. Now, the...
no blow up for you.
Yeah. Not inviscid limit. Now the lambda is Carthago. Nu equals 1. Okay? We're talking about Navier-Stokes now. So I'm talking about regularity for Navier-Stokes. And if you assume that the vorticity is coherent, meaning that its direction field is Lipschitz, let's say, then there is no blow up. And that, how is that achieved? Well, there is something called vortex reconnection. When things start, vortices get together very close, this is an observation, numerical and physical, then they reconnect, they become parallel. So, and that rotary connection needs the rate of strain. It's not a viscous phenomenon alone, it's a nonlinear phenomenon that includes the other part of the gradient of a velocity, the symmetric part. And the rate of strain needs the pressure. So there is my little Delenda est Carthago. Let's return to what we talked about. how does the 2D inverse cascade work? How do we, even for simple vortices of the same sign, how do they merge? Everybody who does any numerical calculations in 2D will tell you it happens, but no mathematician has enough information to do it. And does this mean that we can produce the average friction, the thing that I was talking about, having bounded solution in the limit of zero viscosity? So the analogous thing for this is a turbulent eddy diffusivity. So can the nonlinearity provide an average friction at low wave numbers in 2D and at high wave numbers in 3D? Okay? And then, is there a well-defined inviscid limit? Even for short time, longish time is preferred, but even for short time in 2D in half space. Because, in general, the information provided by a smooth IVP Euler solution is lost. So really, there is no nearby Euler flow. You insist, I have the same initial data, I start for a short time, and I would like to say I'm staying near this particular Euler solution. But when you do the analysis, you discover you're nowhere near that guy. You forgot it. So is there even a well-defined inviscid limit? Okay? So I will conclude in Romanian. La mult, Sergiu.
Thank you, Peter. Any questions? Yes.
Would you people from what you expected that there should be some generation of vorticity below the circle? Have you an idea of how to say attach it to the mathematical model?
There is a way of writing the Navier-Stokes equations so that you know that from any, okay, so there is an inviscid limit from functional analysis on the boundary. How to generate it from actual models?
I don't want to get the inviscid limit because I know that below the circle should be wrong.
Yes. So, well, but the production of vorticity, well, there is production of vorticity from the boundary layers. Having models, this is part of having examples and models in which this is generated. There are some ideas, for instance, you can do it, but it's very, very weak. So by very weak, I mean, essentially, you can produce, and this is an idea of Gautam-Meyer, you can produce a little bit of vertical motion if you put even point vortices with the boundary layer. So you can create explicitly, you can produce that there is but that vanishes with viscosity. So that effect is very weak. So I don't know, in other words. I mean, this would be a very, very nice result, just simply, essentially disproving the inviscid limit in any condition.
I mean, outside the conditions for which you have good.
Any example that rigorously disproves it, even for short time, even for half space.
In your first theorem of invisibility, when the finite time of boundaries, you talked about a gap, zero.
Yeah.
What was new one?
New one was, for any initial data, I mean, it's very well known that if viscosity is strong enough, then things will be regular and go to. So it's a small data new one. You can have small, if the initial data is fixed and you have only viscosity to play with, then you make the Reynolds number small enough by taking viscosity large enough. So the small Reynolds number problem is always globally nice.
How would you fit? How would you fit the separation of a boundary layer into the discussion?
So this is the same question as Laura. So essentially, the separation of boundary layer is violation of any of these conditions, in particular creation of vertical gradients. So the wall stress, shear stress.
Should it happen instantaneously, or does it only happen after a while?
Well, that's again, at this point, I think that there are reasonable solutions for which it should happen, quote unquote, instantaneously. In other words, for which there is not even for a short time the inviscid limit. But that's hard, right?